This is my RoboJib, and it's an all-in-one piece of camera equipment that moves the camera in all directions, allowing more creative freedom with super unique angles, dynamic camera movements, and a more efficient filming workflow. As someone who makes a lot of videos for social media, one of the biggest bottlenecks in the content creator workflow is the act of physically filming. For anyone who works with video, the creative freedom, technical quality, and efficiency of filming is typically determined by how much camera gear they have. Traditional cinema typically works with large budgets so they can afford the price of highly specialized equipment. Casual users have access to cheap and easy to use equipment. But for that middle zone, that prosumer market, cinema equipment is much too expensive and consumer equipment is just too limiting. Personally, I started making YouTube videos with an iPhone and a cheap tripod. And as my channel started to grow, I got ad revenue and sponsorships, meaning that I needed to increase the quality and quantity of my videos. So I started upgrading my gear, which helped me a lot. However, as I continued to grow, I found that the equipment that I needed to create the shots I wanted was super expensive and difficult to use. And it's not just me who thinks this. I interviewed 2 other content creators and found their opinions on it. First up, this is Nicholas Grant, a full-time YouTuber with 628,000 subscribers focusing on drone and camera content. Second, this is Jaden Kogostanis, a casual YouTuber with 4,000 subscribers focusing on building his own startup with YouTube videos on the side. From these conversations, 3 main things stood out. Number 1,
equipment needs to cut down on production time.
Number 2, camera equipment needs to be
Intuitive and simple to use.
And number 3, camera equipment needs to be
Versatile to allow for creative freedom.
So here's what I propose: an all-in-one robot motion control system with many degrees of freedom connected to one system running software to control them all using an intuitive UI. This is not a new idea. What's normally used in the filmmaking industry is an automotive robot arm repurposed to hold a camera. Actually, this is everything I could ever want, and I would buy one, but it's $10,000. So why is it $10,000? Firstly, ultra powerful motors. The further out you hold a load, the bigger the moment, the greater the force needs to produce. Number 2, ultra precise movement. For cinema use, you need millimeter perfect precision. You have to get the framing right, and it also makes it a lot easier for the VFX team. So, every gear, belt, and chain needs to have absolute perfect tolerances, which increases the manufacturing cost. Okay, firstly, we do not need ultra precise movement. I'm not building a cinema quality rig. This is for content creators and similar professions. So getting the framing off by half a centimeter is no big deal. This means that I can manufacture my parts using 3D printing instead of CNCing them, cutting down on time and cost. Secondly, the use of ultra-powerful motors comes from an inherent flaw with the structure of a robot arm. I tried multiple times to figure out a solution which is cheap, low power, and simple. The first experiment was a mini pan tilt system, and that proved that very short limbs allows for better movements with smaller motors, but this heavily limits the functional freedom of movement. My second experiment consisted of building a frame and mounting it upside down, which allows gravity to work for the motors. However, I found this gravity hack only applying when the motor is close to the table, which limits the versatility and the functionality. From these 2 experiments, I concluded that the goal of the system is to freely maneuver a large load in a set space. With this robot arm style structure, you just always need a really powerful motor, and that is why there is no cinema robot in the prosumer price range. It's just an inherent flaw in the design. So instead of trying to minimize a load on the motor, I actually opted to add more weight on the other side of the load to counterbalance it. This reduces my max acceleration and puts more strain on the joints on the system. However, it allows me to use affordable motors. This still is not a new design. It's based off of an existing piece of camera equipment called a jib, typically used to create large sweeping shots, but people have motorized it to create low-cost motion control systems like this one by Digital Bird. At first glance, it can seem that the RoboJib has already been done, but all of these designs are missing something: true 3D movement. Due to being placed on a swivel, the camera can only move in circular paths. But my design will feature a 5th push-pull axis, which moves the camera forward and backward, allowing linear movement parts so then it can properly mimic other forms of camera equipment. So you don't have to go out there and buy dollies and sliders. You can just have this one thing. So I've chosen to pursue a jib style piece of camera equipment over other designs as it's cheaper, simpler, and allows for a longer range of motion. These qualities give me the best opportunities to fulfill my design criteria. First, let's tackle the mechanical design. The design can be split into 3 main assemblies: the base, the midsection, and the head. Let's start with the base. We'll need a big sturdy tripod with rubber feet and a mount that we can modify. Designing around complex geometry such as this inner bowl is really difficult. By first designing and printing basic features to test the fit, then adding on more complex features, this iterative approach allows for a perfect fit to be achieved in a couple iterations. These parts also need to be extremely structurally secure and support the weight of the jib, so the material is super important. So just doing some secondary research, PLA plastic is cheaper, stiffer, but melts at 60 degrees. PETG plastic is more expensive, stronger, and melts at 80 degrees. I will be using PLA mainly for this build, as I'm confident that with good mechanical design, it can very well bear the load. Next is the electronics housing. This part does not hold any load, so I freely positioned components and added holes for ease of use. In future revisions, I would really like to opt for a more aesthetically pleasing enclosed design for a more professional and safe user experience. The base will also house the main rotating motor. The big motor fits in securely and I use a 1:9 reduction gear ratio with a planetary gearbox using helical gears. Motors of this kind do not perform well when spinning slowly, so the gearbox accommodates this weakness. In order to support the weight from the tripod instead of from the motor, I used a lazy Susan bearing and used a vertically free coupling. I experimented with two different designs of coupling. The first was a cross design, which was simple to design and manufacture. However, over time the edges wore and there was a significant amount of wiggle. My second design was a spur gear, as multiple rounded protrusions meant a uniform distribution of force, leading to significantly less wiggle. Now, let's go through the midsection. Two heavy-duty servos are used to control the tilt of the arm. I chose servo motors for their high torque and small size. One of the more difficult problems in this project was the mounting of the linear actuator to the servos. There are many parts to mount and lots of forces happening in many directions. After some failed designs, I switched my material from PLA to PETG and set it on a snap fit offset with screw-in tighteners. This component here is the perfect example of the benefits of an iterative approach with 3D printed technology. Printing it bottom up allows the 3D printer layer line to sit parallel with the tension of the snap fit, fully utilizing the elasticity of PETG, meaning an extremely strong, low cost, and highly effective mounting system. Now, the head. First, a little experiment is needed to test the basic kinematics of the system, and with this experiment, I realized the camera must be aligned with the axes of movement, so that a rotation in the pan or tilt only results in rotation and not any excess 3D movement. My first iteration tested all of the connections with a housing for the GoPro, and I realized that the assembly was too heavy and there was no resistance to twisting forces. I simulated the stress on the body to determine the optimal placement of materials and printed it in PETG. I added peripheral rods to stabilize the head, and I tried 6mm and 9.5mm eucalyptus wood rods, but they were too flimsy. I didn't want to use metal as it was too heavy, so I settled on a 12mm aluminium tube that is only 1mm thick. Ultimately, I heavily reduced the weight and heavily increased the stability of the head assembly. Next is electronics. In my criteria, the arm needed to be simple to use. Thus, it should have elegant power, wiring, and programming solutions. Ideally, you got one connector, one on-off switch, neatly routed wires, all connected to one central circuit board. That's the ideal, and we're gonna strive towards that, but obviously some compromises can be made. My third experiment included testing the power draw of the largest motor in the system under different loads. By connecting it to my computer, I could see the current draw, and it was in between the range of 1 to 10 amps. So, the first compromise is having more than one circuit board. In retrospect, I should have selected a smaller motor. To power and control this monster, I need a separate heavy-duty circuit board. After that, I have two main iterations of electronics and power system. My first design, I used the tool KiCad to design a circuit board and the tool WeBench to generate an appropriate power supply. I ordered a custom circuit board and my components, and upon testing of the circuit board, I observed the power supply to be extremely weak and further experimented to find that the soldering of the chip was done insufficiently. Thus, I concluded that I should go for a ready-made solution rather than trying to design my own circuit board from scratch. For my second design, I used this generic robot controller board, and I also added these two buck converters which help with supplying the power to the servo motors. One problem that I ran into was the wiring and interface of the servo motors. These are quite powerful, however, they are inaccurate. Sending the same signal to both motors results in slightly different angles, leading to them fighting each other, which spikes the current like crazy, which is bad for controlling them, places unnecessary stress on the structure, and it even burnt my board one time. What I did to solve this problem was cut the sensor from motor 2 and wire the sensor of motor 1 to motor 2. Then I flipped the motor connections of motor 2 to have mirrored movement. This leads to perfect control of both motors. The exposed circuits help me to design, develop, and debug the circuits. However, moving forward, I need to better integrate the mechanical and electrical systems. This will reduce the risk of using the system and simplify the design language, naturally leading to a more intuitive system. Now onto programming. Now that it all physically works, we can program some basic moves, which is pretty cool. However, this is supposed to increase the efficiency of the creator's workflow, and right now, I'm literally writing code line by line, the movement coordinates, and then connecting it to my computer, then uploading it, then disconnecting it, and then running the code. We need to remove as many steps from this process as possible to make the user experience as seamless and as efficient as possible. Firstly, let's get rid of the cable and the constant upload, re-upload cycle. I need wireless functions, and I can either use Wi-Fi or Bluetooth for the control. Doing some online secondary research, Wi-Fi is long range, more information, and high latency. Bluetooth is shorter range, lower latency. However, the deal breaker for me is with Wi-Fi, you can create web servers, which gives you the opportunity to create simple web graphical user interfaces, which any device can connect to. Going forward, I will develop a wireless web GUI, which can be used to control the system intuitively. In all, I would say that the RoboJib does increase my creative range, allowing me to create super fast, dynamic, and unique shots. And although the software isn't fully developed yet, it's still faster and higher quality than what I had before. I used to sit on a skateboard and hold a camera to create shots like these. But now I can just use a RoboJib. And in terms of simple to use, well, this thing is not simple to use at all. You need a lot of technical knowledge to be able to operate this thing. So overall, I'd say it reaches about half of the criteria. So here's what I'm doing going forward. First, I'm developing the wireless control functions. This will increase the ease of use significantly. Second, I need to tidy up all these wires and circuits because they can't be hanging out like this. Third, I'm going to optimize the weight of all of these bodies so we can move better and also make the tolerances better to adjust for all the minor wiggles that there are in the system. Fourth and finally, I need to create a universal mounting dock to accommodate for all sorts of different cameras. A GoPro is just not going to cut it anymore. This RoboJib has great potential to fulfill a genuine need. The prosumer market for camera equipment is growing, and I know that at least personally, I'll be using this RoboJib to be creating my content going forward.